All right, today your objective is to learn the properties of regular polygons, which you will define regular polygons in a second, in order to identify the interior, exterior angle measures, and the number of diagonals and symmetry lines. Your other small objective is the students will learn the definition of rotational symmetry in order to determine the magnitude of rotational symmetry in objects. Okay? So your agenda is you're going to complete the lesson on regular polygons and rotational symmetry. This is a video, obviously. And then you're going to turn that into the red bin. You're then going to complete the lesson and additional worksheets on factoring. So you're going to watch 2 separate videos today. And you're going to turn that work into the green bin. And then if you have any other missing assignments, you can do them. All right, so regular polygons mean all sides equal. They're the nice pretty ones, and they're pretty because all their sides are equal. Their interior angles are also equal. And your exterior angles are also equal. So that's what makes them very nice looking, is all the sides are congruent, all the interior angles are congruent, and then all the exterior angles are congruent. So completing this chart, our regular polygons, we have the equilateral triangle, the square, which has 4 sides. You have the pentagon, which obviously has 5 sides. And then the hexagon, which has 6. You all should know that. So then an n-gon just has n number of sides. So looking at this chart, the sum of the interior angles of a square you should know is 360. Pentagon is 540. Hexagon is 720. And the n-gon, the formula, if you remember, is n minus 2 times 180. That will get you any side. So then if you're looking at the measure of one interior angle of an equilateral triangle, one angle is 60 degrees. You get that by taking the sum dividing by the number of sides. 360 divided by 4. So each angle in a square is 90 degrees. Each angle in a regular pentagon, you should be able to figure this one out. 540 divided by 5. And that's going to give you your angle measure. So you're going to need to fill that in. And then the hexagon, same thing. You need to do 720 divided by 6. And obviously I would fill that in on your chart. So if you have any other n-gons, so say a decagon with 10 sides, a nonagon with 9, you simply take the sum, n minus 2 times 180, and you divide it by the number of sides. Okay? Now, if you were to get the measure of one exterior angle, we're going to see what all the measures, the sums of exterior angles is always 360. So you're always doing 360 divided by something, and it's always going to be 360 divided by the number of sides. So 360 divided by n will get you for any number of sides. 360 divided by 3, 120. 360 divided by 4, 90. 360 divided by 5, you should be able to figure that out. 360 divided by 6, you should also be able to figure that out. Hopefully you can see the relation between 60 and 120. They add up to 180. 90 and 90 add up to 180. These two numbers should add up to 180, and these two numbers should add up to 180, which means they form a linear pair. So symmetry lines are however you can fold a figure onto itself. So if you draw a line straight through it, whatever on the left is exactly on the right. So an equilateral triangle has 3, 4, 5, 6. So a regular n-gon just has n number of symmetry lines. Okay? All right, the diagonals are something we're going to talk about, and there's actually a formula we're going to use. An equilateral triangle has 0 diagonals. A square has 2. A pentagon has 5. A regular hexagon has 9. Okay, so the formula for this is n times n minus 3 divided by 2. That will get you your diagonals. So let's figure out what the diagonal is. A diagonal is just from corner to corner. So in a square, this would be a diagonal. It would also be a symmetry line. And this would be a diagonal. So those are your 2 diagonals. But then if you wanted to put your symmetry lines in, you would probably have a symmetry line right about there. It's just an estimate. And then a symmetry line right about there. Okay? So you have 2 diagonals and 4 symmetry lines. In the pentagon, you have 5 diagonals. So from corner to corner, we have, there's 1, 2, 3, 4, 5. Looks like a star. So again, you have 5 diagonals, 5 symmetry lines. Now I'm not going to draw all the diagonals of this hexagon. I'm going to point out that if you draw a diagonal here, there, and there, you're splitting that angle into 4 parts, and they're actually going to be 4 equal parts, we'll see. And guess what? You can cross out this one. Okay? And just make sure you put in your, hey, my hexagon has 6 diagonals but 9 symmetry lines. So a symmetry line for a diagonal, or I'm sorry, a symmetry line for a hexagon, let me use a different color, could be something like this, which you notice is not a diagonal because it doesn't go from corner to corner. Which leads us to when you have an odd number of sides, so for example, a triangle, a pentagon, a heptagon, which is 7 sides. When you have n number of sides, your symmetry lines are the bisectors of the angles, and there are n of those. So okay, so I will see this. If you're looking at your pentagon, your symmetry line, I'm going to draw in pink. This pink line could be a symmetry line, which means it's bisecting that top angle, but it's a perpendicular bisector to what it intersects. Here, bisect that angle, perpendicular bisector to the other side. Okay? So again, your symmetry lines of odd sides are the bisectors of angles, each of which go through the perpendicular bisector of the opposite side. And then when n is even, your symmetry lines are the bisectors of opposite angles, and there's n divided by 2 of those, so half of them. And they're also the perpendicular bisectors of the sides. And there's also n divided by 2 of those. So you can see up here in our hexagon, whoops, not that one, that symmetry line is the bisector of the sides, not of those angles. But this symmetry line coming in hot is, I could bisect those angles, and that's also a symmetry line. So it's a little complicated, but I think you can do it. All right, so if you flip over, we're going to look at a couple examples. So a regular pentagon means all your sides are equal, all your angles are equal, all your exterior angles are equal. So I would maybe make a note that the sum is 540. Each interior angle is 540 divided by 5, which is 108. And then each exterior angle is 72, 360 divided by 5. And I want you to make a note. You're going to draw all the diagonals from angle A. And I knew I want to draw from angle A because the next question is asking for the measure of BAC. And A is the vertex of that angle. So that's going to tell us where to draw from. Okay? So I'm going to draw my diagonals from A. There's one corner to corner, another one from corner to corner, and that's all that goes through A. The good thing about diagonals is it divides this angle now into equal parts. So whatever this little piece is congruent to that little piece, which is congruent to that little piece. Okay? We also know this whole angle is one interior angle of a pentagon, which means that's the measure of B, not A, AE. And that angle equals 108. The angle we want to find is BAC. So we got to find the measure of that guy. Well, lucky for us, the diagonals divide the interior angle into 3 equal parts. So we know the whole is 108, and we're just going to do 108 divided by 3, and that should get you to 36 degrees. Okay, so moving to your hexagon, you should know your sum is 720. Okay, each interior angle would be 720 divided by 6, which is 120 degrees. Each exterior would be 360 divided by 6, which is 60 degrees. And hopefully you can figure out, we're going to draw all the diagonals from angle E because that's our other vertex, and see how many it's going to split into. So from angle E, we have corner to corner, corner to corner, corner to corner. Okay? So you can see that it got split into 1, 2, 3, 4. 4 equal parts. And you should also know that there is one angle of a hexagon. So the measure of angle DEF is just one angle of your hexagon, which is 120 degrees. But they want us to find the measure of DEB. Oh, shucks. DEB. Okay. So from here to there. So how many parts? That's 2 parts. So we could just say it's half of 60 because it includes 2 parts. So what you could do is you could do 120 divided by 2 because we only need half and to get 60. Or you could find the measure of each little part. So you could do 120 divided by 4 to get 30, and we needed 2 parts, so that would get you back to 60. So each little part, again, is 30 this time. But because we wanted DEB, we needed 2 parts. So 30 plus 30. Okay? That concludes regular polygons. That's really all you need to know. And the last little lesson is on rotational symmetry. So rotational symmetry, you want to think of the game perfection. If you remember perfection, it was you have to fit the figure into that little piece. So if you're looking at a piece like this, you got to think how many times could you turn it so it would still fit in to the little hole. There's some that you could turn and do in different ways more than others, and that is because of its rotational symmetry. So rotational symmetry is when a figure can be rotated onto itself. Or turn. And this is super duper easy. You're going to have a picture like this on your test. It's probably going to be a flower or a star or something, and that's going to be your hint to use what we do now. So you want to know what's the smallest magnitude of rotation that will map this figure onto itself. So if you were thinking about turning that figure, how many degrees would you have to turn it so it would still look exactly like it does? All you have to do here is count how many petals or pricks or whatever you want to call them there are. So there's 5 there, and all you do is 360 divided by the number of petals or whatever they are. Okay? And there you go. That means you'd have to turn that star 72 degrees to be back in its exact spot. And this one, smallest of rotation, just count the petals. I suggest you put the numbers on the petals so you don't miscount and miss an easy question. Okay? 8, so 360, because we're going to turn in a circle, divided by 8, 45 degrees. Okay? All right, your goal is to do this problem on your own and this problem on your own. And then remember, you're turning this into the red bin. And then you're going to start the next video on quadratic.